Welcome to qubit-lab.ch. Quantum chemistry is one of the most concrete use cases for quantum computing because the system you want to simulate is quantum from the start. In this series, I zoom in on one practical task from battery R&D, estimating a molecule's electronic ground state energy. In this first video, I give you the orientation, why it matters for batteries, how orbitals lead to an electronic Hamiltonian, and which algorithm families exist to estimate the ground state energy. In the next video, we compare VQE, adapt VQE, and phase estimation-based approaches like trotterization, and the state-of-the-art qubitization approach. So why does quantum computing add value here? It comes down to how the state of a molecule scales. Classically, even a single molecule becomes hard quickly. With n spin orbitals, the electronic wave function lives in a 2 to the power of n dimensional space. So exact simulation scales exponentially. A quantum computer can represent that same many-electron state natively across n qubits. Instead of explicitly storing and updating all amplitudes, we implement the physics as a quantum circuit, which is why quantum methods can scale significantly better for electronic structure problems. Why does quantum computing matter for batteries? A lot of modern cathode materials use transition metals like cobalt, nickel, and manganese. Their d electrons can be strongly correlated, which is exactly where many standard electronic structure approximations become sensitive to modeling choices, especially for redox energetics and defects. If we can improve key electronic energies, it directly affects practical decisions like electrolyte stability, interfacial reactions, and anode safety. The motivation is simple. Better electronic structure accuracy can translate into better screening and better materials decisions. Okay, so we've seen where classical models can become sensitive in battery materials. Now let's zoom into the core object behind all of it, the electronic Hamiltonian. From here on, everything we do is basically build H for a chosen geometry, then extract the ground state energy from it. In a molecule, those atomic orbitals combine into molecular orbitals shaped by the geometry of the molecule and the interactions between atoms. Molecular orbitals come with energy levels. Some are bonding and stabilize the molecule, others are antibonding and destabilize it. The ground state energy is the energy of the lowest energy electron configuration across these orbitals. In practice, we first determine the molecular orbitals classically, and then we build the electronic Hamiltonian in that orbital basis. These orbitals define the basis, and the Hamiltonian defines the rules of the electron problem. The quantum algorithm then uses that Hamiltonian to estimate the lowest energy many-electron state and its ground state energy for those given orbitals. Now we switch from chemistry language to a form a quantum computer can work with. There are two common viewpoints. In first quantization, you think in terms of electron coordinates. Where are the electrons in space? In second quantization, you switch perspective to orbitals. You don't track positions directly, you track which spin orbitals are occupied. That's why we use creation and annihilation operators. They are basically bookkeeping operators. Add an electron to spin orbital p or remove one from spin orbital q. And the Hamiltonian becomes a compact sum of these operator products, with coefficients coming from the 1 and 2 electron integrals in your chosen orbital basis. But qubits are not fermions, so we still need one more translation step. We map those fermionic operators to qubit operators using Jordan-Wigner, and after that the Hamiltonian turns into a weighted sum of Pauli strings. That Pauli sum form is the handoff point. It's what VQE, trotterization, and qubitization base methods actually take as input. Before we look at specific chemistry algorithms, it helps to place them in the broader hardware timeline. We are currently in the NISQ era of quantum computing. Today's quantum devices are noisy and not fault-tolerant, so circuit depth and complexity are limited. That's why most practical work focuses on hybrid quantum classical workflows. Fault-tolerant machines with logical qubits should arrive later, first capabilities late 2020s, with broader impact more likely in the early 2030s. So for now, we optimize for what fits on NISQ hardware. Now that we've placed today's hardware limits, let's look at what a realistic workflow for molecular ground state energy looks like in the near term versus fault-tolerant. In the near term, the practical pattern is hybrid. Use classical screening to narrow candidates, then apply quantum methods on a small active space, and finally validate and refine with classical tools. The point is not full molecule simulation yet, but targeted subproblems where quantum can add signal. That's why VQE and Adapt VQE is the best fit for NISQ today. For fault-tolerant machines, you shift to high-precision phase estimation approaches. Trotterization is the older route but can get deep, while qubitization is the more advanced option with better asymptotic scaling and no trotter step size error. Given those near-term constraints, here is the short list of algorithms that matter, split into what we can do now versus what becomes relevant once we have fault-tolerant hardware. At the top are the NISQ options. VQE is the baseline, short circuits, but lots of measurement shots, and results depend on ansatz quality. Adapt VQE is often the more practical focus for now, because it grows the ansatz step by step and can converge more efficiently, although it is still shot-heavy due to the additional gradient measurements. Below that are the fault-tolerant paths. QPE with trotterization can deliver high precision, but circuit depth grows quickly, and you trade accuracy against trotter discretization error. Plus, you still need a good starting state. QPE with qubitization is the next iteration. It removes the trotter step size error and has the best known asymptotic scaling, but it relies on a solid block encoding and, again, a good initial state. In the next video, we will examine these 4 algorithms in detail, step by step. For the next episode and more material on quantum computing in business, finance, and chemistry, visit qubit-lab.ch. Thanks for watching and have a great day.